This is the video for 4-3 Day 1. It's the first of the videos. Please be sure to watch and take notes on all of them in order to get all the material and to do some practice. As usual with videos, stop it, go back, listen to a section again if some of the information isn't making sense the first time. 4-3 Day 1 talks about derivatives of inverse trig functions. Not the derivatives of the trig functions themselves that you've done before, but of their inverse function. So let's back up and remind you of some things from pre-cal that you know about inverse functions. Inverse functions take the input from a regular function and switch it to the output and vice versa. What that means, and we'll use this tangent graph as an example, is that this is part of a tangent curve, the blue curve. If the point AB is on that curve, whatever the coordinates are, on its inverse, the inverse takes as input the old y value, okay, which is now its input, and gives you back your original input. For instance, on tangent, the normal input to tangent, the x value is typically an angle measure, and the output from tangent is a ratio, a tangent ratio at that particular location. So on inverse tangents relationship, it inputs the ratio and outputs the angle measure. Inverses can be found for any function. They were the undo function. They're the function that allows you to undo all the things done to a function and come back to where you started. Any inverse function then can be found by switching the y's and the x's, the inputs and the outputs. So when graphed, they end up being a reflection across the y equals x line, across the line where y's and x's are the same. So on this picture, this dotted line on the graph that you see is that y equals x line. The reason that's the reflection line is any point on here already has identical x and y coordinates, and they would not need to move to do the inverse. So 5, 5, 6, 6 would be on that reflection line. So the other thing to keep in mind is now starting to think in calculus terms. If a tangent line exists at a point on a curve, and when it exists, it would exist at the x coordinate a, and then whatever the y coordinate is when you plug it in. Then the tangent line would exist to the curve's inverse. Okay, so it would be tangent to the graph of f prime at the point and switch the input-output. So if we had a tangent to the blue curve, we could switch it to being a tangent at the green curve's reversed ordered pair. So if it's tangent here at AB, it'd be tangent to the inverse at BA. There's one other relationship that would happen as well. Whatever the slope of the tangent line is for the blue equation, it would be the reciprocal for the green equation. So while this isn't the numbers themselves, if the slope of the tangent here were 2, then the slope of the tangent at the green point would be 1/2. And we'll get into that a little bit more as you go through some of the calculations and things, but it's just worth pointing out, and that's what this last relationship says on this slide. We're not going to get into it too deeply. It's telling you in the box that if we do the derivative of the inverse function, and that's what that notation is, they're talking about the derivative of the inverse function, okay, that the slope value for that should be the reciprocal of the derivative value for the original function. So the slope of a reflected tangent line from the regular function to the inverse would be the reciprocal of the slope that we would find. So for instance, on this graph, I've got cosine and then I've got inverse cosine graphed. The red one is cosine, the blue one is inverse, or arc cosine. That's the other notation for inverse. So when you see that, you need to be flexible enough to realize that the other notation for inverse cosine would look like that. Same function, same meaning. So whatever the slope at a particular ordered pair is, the reciprocal slope would exist at that point for the reciprocal, or for the inverse graph. So the derivatives. Instead of just giving you all 6 derivatives, which seem to come out of nowhere, we're just going to find the derivatives for inverse sine and inverse cosine, with the understanding that if the original function, theorem 1 up here, if the original function is differentiable at every point on some interval, every set of x to x values, and is never 0 on that interval, then the inverse also is differentiable at every point on that interval. So sine is differentiable on a lot of intervals, and therefore inverse sine is as well. So we're gonna find inverse sine's derivative by thinking through some things we know from your background. We're gonna derive two of them and then we'll share the rest of them. So I'm looking at y equals inverse sine of x, and I'm gonna come up with an equivalent equation to that I can think about a derivative for. So that's the original that they gave me. In thinking through what that means in terms of derivatives, that means that x would come out. I'm switching that role of input and output, so these two are equivalent. I haven't started to do any derivatives yet, I'm just rewriting my original function. I'm going to use implicit differentiation since I've got two sides of this. So by implicit differentiation on this side, the left-hand side is really easy. So the slope of the derivative of the left-hand side is 1. The derivative of the right-hand side, well, sine's derivative is cosine, but since I don't know the y function, I need to talk about the derivative of the y function there. So as I solve for this, I'm going to get dy over dx, the derivative of the y in terms of x, is 1 over the cosine function. However, that's not really in terms of x, that's still got the y value sitting in there. So before we can come up with the final derivative that's going to be used for sine's inverse, we need to go back to some identity things from last year. So one of your trig identities that you used all the time, the most common one that you used, was that sine squared of any angle plus cosine squared of that same angle had to be 1. So we're going to try to put y in terms of something else so that we know what we've got. So solving this one a little bit, I'd have that cosine squared of y would be 1 minus sine squared of y, just doing a little algebra. And then I would take the square root on both sides, so I'd have that the cosine of the y function is the square root of 1 minus sine of the y function. And then I want to go back to what I have in the very beginning. I want to go back to this fact. X is the sine of y. So as I go through this, sorry, I lost my squared right there. As I go through this, I'm going to say, okay, instead of sine y in there, I'm going to put x's back in because I would like cosine y's function in terms of x's. So it's going to be 1 minus, instead of sine squared, x squared. So coming back over to my derivative, instead of 1 over cosine, the derivative of the sine inverse function is 1 divided by 1 minus x squared. So find the derivative with respect to x is what they asked us to do. So we couldn't stop here and leave the y's in there. We needed to move it around. So the derivative of sine's inverse function, then the derivative here would be 1 over, and it's going to be the square root of 1 minus x squared. Go back and look at any of the pieces of this that you might need to and see where we did that. And we'll do it again for cosine, and you'll see they're very similar and they have a lot of features in common. It's the only two we'll do that for, and then we'll show you the rest of them. They can all be done this way with some trig identities. So we're going to try to find the derivative of inverse cosine, arc cosine. Rewriting that so I've got a function that I'm feeling okay about. This would be the normal cosine function, okay, inverse cosine of x, that's just notation switch. But what inverse cosine really means is switch the role of input and output, and then I can just have a cosine function. So I haven't started to derive yet, I've just switched it around. Now I'm going to start to do implicit differentiation on both sides so that I can start to come up with my derivative. So the derivative of x is 1. The derivative of cosine y, well, cosine's derivative is the opposite of sine, and then I need dy dx because I don't know the derivative of the y function. Moving that around, I would have so far that the derivative of that inverse function would be equal to 1 divided by negative sine of y. Again, we aren't going to leave it in terms of y because we need the derivative in respect to x. So I'm going to come back to a Pythagorean identity, the same one we just had. Sine squared y plus cosine squared y, I need a y in there, equals 1. Now I want to move this around and solve for sine of y so that I can get a replacement value. So I know that this is true, so I do know then that sine squared will equal 1 minus cosine squared y. Sine of y then would be the square root of 1 minus cosine squared y. Then I'm going back to the very beginning to this fact up here that says if you have cosines of y's, they can be replaced with or are equivalent to x. So I've got now that sine of y is equivalent to 1 minus x squared, just like I found for cosine. Moving that back over, my final derivative value then for the inverse cosine function, I'm going to move the negative up to the top so I don't lose track of it. And then the denominator, in place of sine of y, I'm going to put the equation of 1 minus x squared. So this would be the derivative for the inverse or arc cosine function. On this slide now, you've got lots of derivative functions to write down, and I would pause the video and get all 6 of these written down. When you get those 6, then return to the video because you're going to want to write down or at least look through and remember some of the domain and range restrictions on the inverse functions. These are the 2 we just did and found their derivatives through some differentiation implicitly. The other 4 then are the derivatives for the 4 other inverse trig functions, the absolute values needing to be in there. When they say du dx, what you need to consider is some of these won't be a simple x value in there, so du dx is the derivative of the interior function. So if they're using a more complicated thing than a simple x, then we're talking about dy dx, du dx is the derivative of that embedded function. So think chain rule. So pause the video, get these 6 accurately and clearly written down, then return to the video to come down and we'll return and move down to keeping in mind some of the domain and range restrictions. Okay, if you're resuming the video, it's so that you can get the domain and range restrictions to think about. Inverse cosine is not defined everywhere. They had to take a small section of the sine graph and just switch its x's and y's so that inverse sine was still a function. When you come to the second video, we'll start to do some practice with this so that you can see how this will look as you use it to derive the derivatives.